Hello, welcome to another module in this massive open online course. So, we have looked at the KKT conditions, that is the Karish-Kuhn-Tucker conditions to solve an optimization problem. Let us look at an application to better understand how one can use the KKT conditions, okay, to solve a practical optimization problem. So, we have seen the KKT conditions. Let us now look at an application of the KKT conditions, and the particular application that we will consider is for optimal power allocation. This is typically a problem that arises very frequently in communication systems. Okay, so this is optimal power allocation, you can say, for communication. Now, what happens in communication is that, let us say you have a set of, frequently what happens is you have a set of parallel channels. So, you have a set of parallel pipes, one can think of this, okay, and so you have channel 1, you have channel 2, and so on and so forth. You have a channel. Let us assume that these are arranged in decreasing order of gains. So, what these are a set of parallel channels, or let us think of parallel communication channels. When I say a channel, it goes without saying that I am talking about a communication channel. So, you have parallel communication channels, and of course, you can transmit at a certain bit rate over each of these communication channels, right, and the bit rate depends on the power that is allocated to that particular channel. So, let us assume that, let us say, the power allocated for first channel is P1, second channel is P2, so on. You have a set of n parallel communication channels, power allocated is Pn. Let us say the gain of first one is alpha 1, this is the gain of channel 1, gain of channel 2 is alpha 2, gain of channel n is alpha n. So, naturally the output power, so this is the input, correct. So, this side is basically information is flowing from left to right. So, this is the input and this is the output, or you can think of it as the left as the transmitter, the right as the receiver. The received power will be, of course, gain is alpha 1, power will be alpha 1 times P1. Similarly, across channel 2, gain alpha 2 times power P2, gain alpha n times power Pn. Okay. So, what this means is you have a set of n parallel channels, across each channel I, the input power is Pi, the gain is alpha I. So, the output power is alpha I times Pi. Now, in addition, for every communication at the receiver, we will have thermal noise, all right, or Gaussian noise, which is typically modeled as additive Gaussian noise. Okay. So, we have this channel, that is yi equals, you can think of it as square root of alpha I, because alpha I is the gain in power, square root of alpha I xi plus ni, where this quantity ni is the additive white Gaussian noise. Mean equals 0, variance equals sigma square. Okay, so noise power is sigma square for each channel. Okay, and so what we have is basically, if you look at the SNR for channel I. SNR is nothing but this is the signal to noise power ratio. This is equal to, well, the received power alpha I pi divided by sigma square. And now one can ask, corresponding to this SNR, what is the maximum rate, information rate, or the bit rate at which one can transmit over this channel, and we have a convenient formula for that, that is given by the Shannon's formula for the capacity of the channel or the maximum information, maximum bit rate of the channel. So, from the Shannon capacity formula, so the maximum is from the Shannon and that is basically given as log to the base 2 1 plus SNR, which for this is log to the base 2 alpha I. So, this is the maximum rate at which information can be transmitted over the, so this is the maximum rate transmitted maximum rate at which information can be transmitted over channel I, and therefore, now what is the, so this is the maximum rate at which information can be transmitted across channel I. Now, therefore, what is the sum rate, the maximum sum rate of information transmitted across all these n parallel channels? That will be given by the sum of the individual rates or the bit rates, sum of the individual maximum rates across each of these n parallel channels. So, the maximum sum rate or the sum rate corresponding to this power allocation corresponding to powers P1, P2, Pn, well, that will be given as the sum of the individual rates, sum I equals 1 to n log to the base 2 1 plus alpha I pi divided by sigma square. And naturally, what we want to do is we want to maximize this sum rate. So, we want to maximize the sum rate. This is your sum rate. Okay. Okay, we want to maximize the sum rate. Now, I am going to do a minor modification here. Instead of choosing log to the base 2, I am going to choose log to the base e into log e to the base 2. So, that is a natural logarithm. So, this then becomes simply the natural logarithm. I am simply going to write it as log or log to the base e. And this thing is, you can see log e to the base 2 is simply a constant factor. So, instead of multiplying, so instead of maximizing the objective function times a constant, I can simply ignore the constant factor. So, I can write this because it is going to be easier for me later. I am just going to write this equivalently, this symbol denotes equivalently as maximizing the sum of the natural logarithm. Okay. So, when there is no base, it automatically means that this is a natural logarithm. Okay. And now, so this is maximized, so equivalent to maximization of this. Now, in any practical system, naturally there is going to be a constraint. What is the constraint? The constraint is we do not have unlimited power. the total transmit power is a fixed quantity. Alright, so the sum of the powers PIs across all these channels has to be fixed, and that is given by the total transmit power of the transmitter, the maximum possible transmit power. Okay, so now we want to maximize the sum rate subject to the constraint that summation I equals 1 to n of PI equals P. So this is, you can think of this as the maximum transmit power of the transmitter subject to the constraint. Now of course, now the other, so this is the, so the sum of the powers across all the channels has to be P, that is the maximum transmit power, and in addition power, remember it is a power, so power has to be non-negative, which means each PI has to be greater than or equal to 0. So you have each PI greater than or equal to 0, which implies, writing it in standard form, each minus PI is less than or equal to 0, or if you look at this vector P bar as P1, P2, Pn, then this has to be component wise greater than or equal to 0. Okay, so this is our optimization problem. Maximize the sum rate subject to the total power constraint and the non-negativity constraint of each power, that each power has to be, each power PI has to be greater than or equal to 0. And you can look at this. Now this is well, log is a concave function, the sum of log is a concave function. So I can, this is a concave maximization of concave objective function, which can write as a convex optimization problem. So again I can write this as, again equivalently, I can write this as minimize I equals 1 to n log to the base 1 plus Pi alpha I by sigma square subject to the constraint I equals 1 to n. This is the equality constraint, and the inequality constraint, that is each P bar is component was greater than or equal to 0, each element Pi is greater than or equal to 0. So this is your convex optimization problem for optimal power allocation. Alright, you are allocating the powers optimally, typically termed as optimal power allocation. Okay, powers are being allocated optimally to the n channels. Okay, optimally powers by being allocated optimally to the n channels. And now we will use the KKT conditions to solve this. Right? How to come up with the optimal power allocation? What are the optimal powers to maximize the sum rate? What are the optimal powers P1, P2, Pn subject to the total power constraint, the non-negativity power constraint, which maximizes the sum rate across this set of parallel n channels. To do that, let us start with again the Lagrangian. Alright, we want to use the KKT conditions. So find, remember, one of the KKT conditions is the Lagrangian. Alright, the derivative of the Lagrangian has to vanish at the optimal. So you form the Lagrangian of P bar lambda bar. Since there is only one equality constraint, there is only going to be one equality, the one Lagrange multiplier nu associated with the equality constraint. So this will be the objective function I equals 1 to n log to the base 1 alpha I Pi by sigma square plus nu summation of I equal to 1 to n Pi minus P or P minus, right, this is the equality constraint, minus or plus lambda bar transpose into minus p bar, or you can write this simply as minus lambda bar transpose p bar, alright, because this is simply p bar greater than equal to 0 component wise, or minus p bar less than equal to 0. Okay. So, this is minus lambda bar. Well, lambda bar, you have one Lagrange multiplier for each inequality constraint, that is basically one Lagrange multiplier for each power. So, lambda 1, lambda 2 up to lambda n. Okay. So, this is the Lagrange multiplier. Now, differentiate this with respect to pi Now, if you differentiate this with respect to pi, what you obtain is basically minus 1 over, that is the derivative of log 1 plus alpha I pi by sigma square, that is 1 over 1 plus alpha I pi by sigma square times alpha I by sigma square, plus along when you differentiate pi, you will have nu, the Lagrange multiplier, you simply get nu, and the derivative of this minus lambda bar transpose p bar with respect to pi, the partial derivative is simply minus lambda I, which is equal to 0. And now this is the key equation. Okay. This setting equal to 0, this is the KKT condition, because the gradient with respect to p bar of lambda p bar lambda, the gradient with respect to p bar of the Lagrangian p bar lambda bar nu has to be equal to 0. Okay. So, this is one of the KKT conditions. Okay. And this implies that alpha I divided by sigma square by 1 plus alpha I pi divided by sigma square plus lambda I equals nu. Okay. Okay, the objective function is, because of this, there has to be a minus here. Okay. Because we are minimizing the negative of the convex negative of the objective function. Alright, so minimizing the negative of the logarithm, which is a convex objective function. Okay. And now therefore, if you look at this, what you have is now remember from the complementary slackness, let us go back to now the complementary slackness. Complementary slackness will be, we have lambda I pi equal to 0, alright. This is, that is either the constraint is slack or the Lagrange multiplier is slack, but not both. Okay. So, lambda into pi equals 0. Now, this implies something very interesting. This implies, now let us consider two conditions. If pi is greater than 0, that is power allocated, that is non-negative power allocated to a channel. Non-negative power is allocated to a channel, then lambda I equals 0, because lambda I pi has to be 0. So, this implies that alpha I divided by sigma square by 1 plus alpha I pi by sigma square equals nu, because lambda is 0, you simply set lambda I in the above equal to 0, which implies that 1 over nu equals 1 plus alpha I pi by sigma square by alpha I by sigma square, which is simply sigma square by alpha I plus pi, which implies that pi equals 1 over nu minus sigma square by alpha I. okay, which also implies, by the way, so this is the optimal power Pi, which is greater than or equal to, which is greater than 0, which implies also 1 over nu is greater than sigma square by alpha I. Okay. So, since 1 over nu is greater than sigma square over alpha I, Pi is 1 over nu minus sigma square by alpha I, and lambda I corresponding eigenvalue is 0. So, this is the optimal power allocated to ith channel. Okay. So, that is 1 over nu minus sigma square divided by alpha I, which implies that 1 over nu is greater than sigma square over alpha I, because the power has to be non-negative. Okay. On the other hand, now if this is your case 2, so the above is your case 1. Case 1 is Pi greater. Now, if lambda I is greater than 0, that is a Lagrange multiplier is slag, this implies that Pi equals 0. Now, this implies now alpha I by sigma square by 1 plus alpha I Pi by sigma square, but Pi is 0. So, 1 plus 0 plus lambda I equals nu. So, this implies alpha I by sigma square, alpha I by sigma square plus lambda I equals nu, which implies that well, lambda I equals nu minus alpha I by sigma square, and the lambda I is greater than 0, which implies that nu greater than alpha I by sigma square, which implies also that 1 over nu is less than alpha I, or which implies that 1 over nu is less than sigma square divided by alpha. Okay. So, there are two cases, 1 over nu less, and therefore, now if you summarize it, what is happening is, if you observe it, therefore, what is happening is Pi, if you look at Pi equals, well, Pi equals, if you look at the condition above, that is 1 over nu minus sigma square by alpha I. So, that is 1 over nu minus sigma square by alpha I if 1 over nu greater than sigma square by alpha I, else Pi is simply 0, if, or you can make this as greater than equal to, actually 1 over, so alpha I, lambda I, in fact lambda I is greater than or equal to 0. So, let me just correct this a little bit. So, lambda I 1 over nu greater than or equal to 0. So, lambda I is equal to 0. Okay. So, Pi is greater than or equal to 0. Okay. Now, it does not really matter. So, basically what it means is, if Pi is equal to 1 over nu minus sigma square by alpha I, if 1 over nu is greater than or equal to sigma square by alpha I, and it is 0 if 1 over nu less than sigma square by alpha I. Okay. And therefore, you can write this Pi succinctly as Pi equals the maximum of 1 over nu minus sigma square by alpha I comma 0, because if 1 over nu is greater than sigma square by alpha I, then the maximum is 1 over nu minus sigma square by alpha I, which is the power Pi. If 1 over nu is less than sigma square by alpha I, then this quantity is negative, and therefore, the maximum will be 0 and the power is 0. So, 1 power Pi equals maximum of 1 over nu minus sigma square by alpha I and 0, and typically this is represented as Pi equals the optimum power, which is 1 over nu minus sigma square by alpha I plus, where x plus equals x if x is greater than or equal to 0, 0 otherwise, or basically if x is less than 0. basically again saying the same thing. This is the maximum of x comma 0. That is the optimal power allocation, that is 1 over nu minus sigma square by alpha I plus. Now, how do you find this optimal? Because you need still find lambda nu, that is from the total power constraint. Okay. So, now how do you find nu? To find nu, you solve summation I equals 1 to n 1 over nu minus sigma square by alpha I plus equals p, that is from the total power constraint. You find this from the total power constraint. Now, you observe something interesting. Let us go back to what we said before. Let us assume without loss of generality that these are ordered, that is alpha 1 gains of alpha 1, the first channel is strongest, greater than second channel, greater than equal to alpha n. Okay. This implies that channel 1 has the strongest gain, highest gain, which implies channel 1 equals strongest, and channel communication channel n equals the weakest. Now, what this implies is, if you look at this, carefully look at this, 1 over al nu minus alpha I divided or minus 1 over nu minus sigma square by alpha I. So, as sigma I increases, observe that as alpha I increases, sigma square by alpha I, this quantity decreases. This implies 1 over nu minus sigma square by alpha I increases, implies that as alpha increases, the power pi increases. Alright. So, more power is allocated to the stronger channel, which implies pi increases, which implies more power is allocated to the stronger channel. Which implies that more power is allocated to the stronger channel. Okay. Now, there is an interesting representation for this. If you look at now, let us look at this representation. If you look at, for instance, a sort of bowl, you can call it, or a area with these kind of pillars. Okay. So, the first pillar is sigma square by alpha 1 corresponding to first channel, because alpha 1 is larger, sigma square by alpha 1 is smallest. So, this is sigma square by alpha 2, sigma square by alpha 3, so on and so forth. Remember, alpha n, alpha is decreasing towards alpha n. So, sigma square by alpha n will be the largest. Okay. So, this is your sigma square by alpha n. Now, if you draw here the level 1 over nu, if you call this as your level 1 over nu, so this is your level 1 over nu, you can think of this as a water level. Now, the power allocated to the first channel is basically the amount of water, that is the level of water 1 over nu. So, if you look at the water level here, all right. One over nu minus sigma square equals by alpha 1, which is the power allocated to channel 1. Similarly, if you look at this level this is basically your 1 over nu minus sigma square by alpha 2. And you see something interesting over here, water level is below the pillar. So, here the water level below the pillar. This implies that Pn, power allocated to the channel, is 0. That is, if 1 over nu is less than sigma square by alpha I for any particular, which means this is your water level, this is the height of the pillar, this implies that 1 over nu minus sigma square by alpha I is less than 0, implies Pi equals 0. So, power allocated to ith channel is 0. Power allocated to I channel is 0. Therefore, this scheme, which you can think of it as a water level poured into a bowl with several pillars, the height of each pillar is sigma square by alpha I corresponding to the ith channel. Power is allocated only if there is a finite non-zero water level above that ith pillar, that is 1 over nu is greater than sigma square over alpha I. If the pillar is higher than the water level, then no power is allocated to that particular channel. Therefore, this is known as the optimal water filling algorithm. So, this is known as the optimal water filling algorithm. So, you can think of this as a water level. So, this is known as the water filling algorithm. This is known as the water filling technique, the water filling scheme for optimal power allocation. Okay. So, if the level of, so this is known as water filling for optimal power, let me just write it clear, the water filling scheme or water filling technique or water filling procedure or water filling scheme for optimal power allocation. That is basically, you can think of it, it is a convex, it is a solution of a convex optimization problem derived or obtained using the KKT conditions, and the complementary slackness plays a very key role. You can see that if 1 over so if Pi is greater than 0, then you have lambda I has to be 0, if Pi equals the, if lambda I greater than 0, if lambda is greater than 0, then Pi has to be 0, and the optimal power allocated to the ith channel is the maximum of 1 over nu minus sigma square by alpha I comma 0, meaning that if 1 over nu is greater than sigma square by alpha I, finite power is allocated to the channel, else the power is allocated is 0. Right. So, this is a nice scheme, or this is the optimal scheme. So, this is the optimal scheme for to maximize, to allocate power across the parallel channels that maximizes the sum rate of communication between the transmitter and the receiver. So, we will stop here and continue in the subsequent one. Thank you very much.